Hello again. In this video, we have another volume by integration problem. This time, though, we are given the curves listed here and told to rotate the region enclosed by those curves about the y-axis, and then find the volume of the resulting figure. So, just like in the last problems, first we want to identify the method of integration that we're going to be using, whether that is disk or washer or shell, which we do with the help of the sketch, right? Getting an idea of the actual figure that we generate, and then along with the help of the sketch, we identify the components of the corresponding formula to the method of integration that we identified. So let's go ahead and draw what would and get an idea of what would be the resulting figure. So we're rotating this about the y-axis, so we're going to end up with something on the other side here. Of course, my drawing is not going to be perfect, just like yours doesn't have to be either. And so we're going to end up with something on this side of the y-axis that looks like this, and then there's going to be, a solid figure that is connecting the two sides. And so we see that we have a gap in the middle of the two highlighted parts here, right? Which tells us that we're not going to be using disk method, and we only have one function. Which means that we're not going to be using a washer method. So if you see the gap and you think washer method, that's good. But for this class, we're only going to be using that if we have two functions, and in this case, we only have one, which is a good indicator of shell method, right? So that's all we really need to know for this class. You could also try to find the inner and outer radii for the washer method, but it won't end up working too well for you, so I'm not going to go into that right now. I just want to save time. But just know that it wouldn't work that well. And all we need to know is that we're not doing disk because there's a gap, and we're not doing washer because we only have one function. So now we know that we're going to be using the shell method, right? Which we know that the formula for shell method is 2 pi integral a to b r h dr. All right, and I just really quickly want to point out that the 2h and the r there, as we know, is circumference. And then, of course, the h is just for height, and the dr is the thickness. And so what I like to do for these problems, just like in the last one, is draw a typical approximating rectangle. And for shell method, it's really convenient because that rectangle corresponds to a lot of, or all of these values here. And it can help us to find the limits of integration. Well, it won't help us to find limits of integration, but it helps us to find circumference, height and thickness, and then we can find limits of integration after that. So let's go ahead and draw a typical approximating rectangle. And remember that for shell method, the rectangle is parallel to the axis of rotation. For disk and washer, we know that it's perpendicular, but for shell, it's parallel. That's just a little rule to remember. So let's go ahead and draw a rectangle that is within the original area enclosed that we highlighted, that is vertical, since we're doing this about a vertical axis. And we see that the thickness of this rectangle is, of course, the difference in x values, right? So we call that delta x, which corresponds to dr in our integral, and that is the thickness of our shell. So we found that, and now we know that everything in our integral, radius or circumference and height, has to be in terms of x, right? So let's go ahead and find our h, our height, which of course is just the height of the rectangle here, which we see that is just modeled by the function y equals x cubed, because we're going from the x-axis up to the function. So that height is just x cubed as we go from left to right there. So we have our height, and we know that our radius is, of course, just the distance from the axis of rotation to our rectangle that we drew. So we see that that is a difference in x values going from horizontally left to right. So radius here is going to be x, and of course we know that for this class, radius is either going to be x or y for shell method. right? And we already identified that we have dx in our integral, so it can't be y, so that only leaves x. So don't try not to get too confused with the radius part. You know, if you have dx, it's going to be x. If you have dy, it's going to be y. That's all you really need to know. Now let's go ahead and find our limits of integration, which of course are going to be in terms of x, and we see that a is going to be 1 here. We start at 1, we end at 2, so we have our integral evaluated from 1 to 2, and of course let's not forget our 2 pi in our formula. And there we go. The hard part's done, right? It took 5 minutes. Now we just need to actually evaluate that integral, right? So we have v equals 2 pi times the integral from 1 to 3, 1 to 2 of x to the 4th power dx. Now we know that power rule is going to help us out here. We have 2 pi times x to the 5th over 5, evaluated from 1 to 2. And what I'm going to do is I'm just going to bring out that 1/5 outside of that to make it a little bit easier on us. And so now we're just evaluating x to the 5th from 1 to 2, which we know that 2 to the 5th power is going to be 32. 1 to the 5th power is going to be 1. So this ends up being 2 times 31, which is going to be 62 pi over 5. And that's it. That is the volume of our cylindrical shell that is generated by rotating the region enclosed by these functions about the y-axis. So notice that for y-axis, for shell method, we're going to have everything in terms of x. So for y-axis integration, our integral is going to be in terms of x, which means that for x-axis integration, it's going to be in terms of y, and it's all the same process, right? It's all the same idea, where you identify the thickness of the rectangle, which would, in x-axis rotation case, be dy, and then you identify everything in terms of y. So hopefully that gave you a better idea of the understanding of the method behind shell method. And please let me know if you have any other questions on anything we talked about through email, and I'll be sure to help you out. Thanks, guys.